All right, Joe. Yeah, you can go ahead and take it away. Actually, let me just say thanks to Joe publicly for stepping in here and filling a gap in our schedule. And I promised Joe that he this would not count officially as his talk for the year because he actually wanted to talk about something else, which he's going to talk about in uh, in April. So
In May.
in May, sorry, in May. So but go ahead and here, Joe. Sorry.
Cool. Great. Well, thanks everyone for joining. I know many of you, but for those of you that I don't know, my name is Joe Hammond. I work at EarthMover. I'll tell you about that in a second. The title of today's uh, presentation for the showcase is Cloud Native Data Loaders for Machine Learning using Zarr and Xarray. And this is a kind of redo of my AMS talk from this year and a summary of a blog post we published on Thursday. And somebody will put it in the chat if you want to take a look at that blog post and you haven't seen it already. But yeah, so let's jump in. Here we go. Cool. All right. So just really briefly, for those of you that don't know me, I'm the CTO at EarthMover. We're a mission focused startup working in the kind of Pangeo space. Our mission is to empower people to use scientific data to solve humanity's greatest challenges. For a lot of the time, that means climate change, weather, disaster, that sort of thing. I started the company with Ryan Abernathy, who also is a longtime Pangean. And we're kind of building a team around of folks that work on Xarray and Zarr and Pangeo from a bunch of big tech companies and weather and climate geospatial places, with the idea that we're really trying to bring some services around scientific data that don't exist. So we're building a product called Array Lake, and the demo I'm going to use today used Array Lake, but I'm not going to be talking about that. We gave a showcase about Array Lake, I don't know, four or 5 months ago. You can go back and look at that if you're interested. So I'm going to talk about two main projects in the open source space today and a few related ones. I expect nearly everybody here knows about Xarray and Zarr, but for those of you that don't, Xarray is a Python library that provides n-dimensional labeled arrays and data sets. It has a data model built around NetCDF, has an incredibly rich API supporting data manipulation and computation. And then Zarr is a library that provides chunked compressed n-dimensional arrays. It's both a specification, and then there's a Python library, Zarr Python. Some of the main features of Zarr is that it's highly scalable. It's a cloud native data format. It's widely used in all of the cloud object stores out there today. And there's lots of Pangeo data in Zarr today. If you go look at the Pangeo Forge project or the Pangeo catalog, you're going to be able to find a lot of Zarr data. Okay, this is obvious, and this slide is now 2 months old, which means it's out of date. But there's a really rapid evolution of AI-based weather forecasting. There's the NVIDIA conference happening this week, bunch of announcements about this. I could remake this slide probably weekly, but the idea is that we're increasingly using machine learning to do weather forecasting and other geoscientific modeling. But specifically in the weather forecasting world, AI has really taken hold, and we're evolving very quickly. Showing some slides here from the Weather Bench project, which is an effort kind of built around this idea that we're doing AI weather forecasting, so we should be able to benchmark those models against each other and figure out what's working, what's not. And we're actually going to use the Weather Bench 2 data in the demo that is in the blog post. So that is it's a data set that includes a bunch of source or feature data that you can use for machine learning model training. All right, so the problem statement in this work is really how do we efficiently train machine learning models with multidimensional array data? So we have data, say, stored in Zarr, follows the Xarray data model. So you have multiple variables. They're 3, 4, 5-dimensional hypercubes. They're stored as these kind of chunked, compressed in-dimensional arrays in object store. And we want to throw them into PyTorch or TensorFlow or something like that. And we want to do that efficiently. And there's a bit of a gap between these two. And one of the things we notice is just that there aren't great like established patterns for how to do this. There are some tools that are in this space, but a pattern for how to do this efficiently is kind of missing. So what do I mean by efficiency here? I think, oftentimes folks care most about, minimizing the time spent training. So how fast can you train your model? I think a lot about how long it takes to develop a pipeline to train a model. Oftentimes, we're all pretty expensive. And so if you save your training, a few hours, but it took you a few days, you probably spent more money on labor getting to that point. So think about that. Cloud spend is another one. So think about, egress charges, GPU time, whatever. And then a metric that a lot of folks use for, training time is just whether or not you can saturate the hardware that you have. So whether that's like network bandwidth or GPU utilization. And that's really what we're going to target here because it does kind of cover the minimized time spent training one. You can only go as fast as your hardware allows. So I think we lack, like I was saying, we lack some good patterns here. So everyone kind of rolls their own approach, and it's hard, on a one-off project to like take a step back and like build a really generic tool. So I always like this cartoon where folks are too busy to take the wheels that are being offered because they're cranking away. And sometimes it feels like that's what we're doing when it comes to machine learning model training. Specifically, I think we've seen in customers and in open source users kind of 3 patterns emerge that I think are worth calling out as things that I'd like to see us avoid if at all possible. So one is the idea that you have to pre-compute your samples and store a second copy of the training data that is, maybe pre-sampled or rechunked or, in some way processed in a way that is like ready just for your machine learning training program. Downloading data before training to a local file system is one that we see a lot. So, you suck all the data down. You might even keep it in Zarr. Maybe you put it in TF records or something, but you put it on your SSD and then you train your model. That often means you have like a pretty long downtime while your GPU is sitting idle while you're, pulling down a few hundred gigabytes or something. It also really limits how big of a data set you can use to train if you're putting all your data on an SSD. And then, finally, like I think just from a labor perspective, like you spend a lot of time, you can spend a lot of time optimizing these. I spent a fair bit of time working on this demo, and it's not a production one. It was meant to kind of show how things go. So I think I have a pretty good feel that like you could spend, a very long time eking out the last bits of performance here. So this past summer, we were working with TJ Vandal and the team at Zeus AI on a collaboration. And the idea was to build a data loader that, loaded data from Zarr, data that's stored directly in Cloud Object Store and stream that data into a machine learning model at training time. We really wanted to be able to use tools that atmospheric scientists know and love. So here I'm thinking about Xarray as a tool that is kind of the lingua franca for how to move this type of data around. And then we wanted, of course, to achieve good throughput. And we were fairly convinced that we needed to build something quite bespoke to do this. I was ready to bust out the like Rust and parallel custom data loader and all of the fancy tools I could think of. But while we were working with the Zeus folks, we kind of realized that like actually existing tools can be put together pretty cleanly and give pretty good performance. So a bit of a pivot here. And so instead of building something new, we kind of assembled this pattern and have migrated a few of the ideas into the XBatcher project. So okay, so this is what the data loader architecture looks like. So you have data and object storage. That data is stored using the Zarr specification. So we'll use the Zarr Python API to load that data. Xarray will talk to that to that Zarr API. We'll use XBatcher to do the batch generation, which I'll talk about in a second, and then we'll use PyTorch as the way to kind of parallelize and coordinate the data loading. Assuming in this case that you're also using PyTorch to train your as your like modeling framework. So, and then, mixed in here is we've got a couple switches that we can use Dask to parallelize, give us concurrent loading of multiple chunks across multiple variables. And we're also going to use Dask's in-memory cache for materialized tasks. So if you've used Dask before, you know that it like processes its task graph. You can actually cache those like intermediate results. And so that's very useful in some cases. All right, so just quickly on XBatcher, Max Jones, who I think is here in the audience, had a talk at AMS a year and a bit ago on XBatcher, so I encourage you to check that out. But the idea with XBatcher is that it's a tool for generating small kind of chips or batches or samples of Xarray data sets. And it's you basically specify the schema for how you want to take your Xarray data set and convert it into small batches. So it's a really lightweight API. It gives some tools for how to combine variables, reshape arrays, and do sampling in certain ways. And it's really meant to sit right between Xarray and your machine learning frameworks. So we're going to use XBatcher. And it provides like a generator interface for like generating the next batch. And it really encourages you to check that out. So what we did is we put together a demo, and I'll drop the link to the GitHub repository at the end of the talk here. But we put together a demo that takes data from the Weatherbench 2 data set. So one of the Era 5 copies there. We're using Array Lake here, but if you're not using Array Lake, you can just point directly at Google Cloud Storage. We're going to pull data from 3 separate variables. Those chunk sizes are about 10 megabytes each. Then we're going to open that data using Xarray and Zarr. Then we're going to use XBatcher to generate these kind of tiny little chips of data. So 3 time points, 48 longitude, 48 latitude, and 13 levels. And then there's a bit of info here. We're going to like throw 4 randomly sampled batches into each training loop. It takes about 0.1 seconds to train that in our example model here. We're going to use PyTorch to do the parallel loading. So PyTorch has a multiprocessing functionality built in. Dask does the parallel chunk fetching and the caching, as I mentioned previously. And then finally, PyTorch will also do read ahead for us. So it will preload batches while you're training, which will allow us to have a batch ready by the time the model's done. So this is the demo setup. And here's a bit of sample code. It's not this is kind of like copied and pasted to show you what the core bits of this data loader are. Like there's a little bit more to it. So don't expect to run this is basically what I'm saying. But so here's a couple highlights. So here's how you create an XBatcher batch generator. So I have an Xarray data set here. And then I specify some, schema parameters for how I want to generate that. So, input dims in the overlap, basically saying like what those patches should look like. I have a custom function here for post-processing that batch. So we have, we take this batch as an Xarray data set. We're going to turn it into a stacked array. And then we're going to like turn the data in that stacked array into a PyTorch tensor. So if you're using a GPU here, like PyTorch will like convert that data into an array on the GPU at this stage. Then we have this XBatcher PyTorch data set. So this is a really thin wrapper around the XBatcher batch generator. And the one thing here is that this functionality is actually like moving in. I think we'll be able to like have this entirely in XBatcher in the future. And then finally, the PyTorch data loader is here at the end. And this is a class that PyTorch provides. You can throw things in like the number of workers and the prefetch factor and the batch size, and then connect that directly into your model. Okay, so that's a little bit here. Finally, the training loop. What we wanted to do is show you how this data loader program evolves, and like when it's reading data and when it's training and all of that. And so rather than use a real model here, we used a sleep function that kind of simulates the time the model would be spending training. And then we do a bunch of like logging, and we'll generate some statistics on like how that all played out. But generally you would have like some like model train step here, like in line 3, but instead we're just kind of like doing our time.sleep here. So what we're really interested in is like how long it takes for, after the model has trained, or in our case, the sleep time, how long it takes to generate the next batch in line 2. So, and hopefully that's near 0, but as I'll show, like out of the box, it's really not. So here's a couple results. Here we have 1 worker, no read ahead, no cache, no Dask workers. This is like just straight out of the box what you get for a data loader. So there's 4 steps here. So you have your setup step. This is like, read the Xarray data from Zarr, set up your data loader, set up your batch generator. Okay, that doesn't take very long. And then anywhere you see purple is time where the program's getting a batch of data. Anywhere you see train, it's that time that it's spending that 0.1 seconds to do the training loop. And then there's 3 epochs here, just meaning we're repeating the pass through the data loader 3 times. And what you see is it's spinning. There's a lot of like white space in between the training loop, which means like the GPU would be waiting in those cases. And the time that this histogram on the right is showing you the time that the model had to wait. So on average, it was like 1.3 seconds or something in between iterations. This is definitely not what you want to see. Like you're going to be like, okay, now's the time I got to go get my SSD and like download the data, because like this is not going to work. So, but the point here is we can actually do a lot better than that. And so that's what this next graph is showing. So we ran that same data loader with a different set of input parameters. The key ones are ran on 32 workers, 4 Dask threads. We told PyTorch to load 3 batches ahead of time. So it was always like reading out 3 batches into the future. And each process had a 10 gigabyte in-memory chunk cache. So if we went back to Zarr for the same chunk that we've already decoded, we just would pull it out of the cache immediately. And now the graph looks very different. So first off, PyTorch takes forever to spin up 32 workers. And I would love it if somebody else could confirm this or tell me what the heck's going on here. But if I set up a Dask cluster with 32 workers, it will take a few seconds maybe. And PyTorch, it takes 200 seconds. I have a feeling that has to do with the shared memory, like the queue that it uses. But I really want to hear what you think is going on there. So that's that. And then you see kind of like complete saturation in the training loop. So this is the same amount of data read. And I'll just show you here, like it took about almost 2,500 seconds to run this program with 1 worker, and it took about 375 with the second. Most of that time was spent just setting up the PyTorch data loader. But you look here at the training step, and like there's very little white between them, except in between epochs when things reset. And the average time, I didn't write it down here, but it's like 0.001 seconds or something. It's like close to what it takes Python to do another loop. So there's a couple batches, probably the first one where it was a little slow, and then after that it got a lot faster. So anyways, this looks much more like what you'd want your training loop to look like. And, we did this with just like a few parameter changes at the PyTorch level. I'll say one last thing on this setup thing. Like, this looks very bad, but if you're going to run your training for a very long time over a very long data set, this setup cost you just do once. And so it's amortized over all of your batches and all your epochs. So like, probably doesn't matter that much, even though it looks bad in my graph. Cool. A couple of conclusions. First, our favorite tools like Xarray and Zarr can be configured to achieve saturation during training. So what that means is you probably don't need to pre-process or download your data to an SSD to get good performance. I say probably because I'm sure there's use cases out there where that still makes sense. One thing to recognize is that most GPU nodes in the cloud today have plenty of CPUs to make this sort of workload possible. So I ran this on SageMaker. It was like a medium-sized GPU. I had 30-some cores on it. It was just like what came with the machine. All you really need to know is like a few things about your program. So how long it takes to load one batch. So you can just use xbatcher in like a time it statement and just like figure out how long it takes to load one batch. In our case, it was 300 milliseconds. You need to know how many batches you want to include per training iteration. Oftentimes this is one, but like if you know that number, then you can like they end up getting stacked together in the input stat. And then how long it takes to train one batch. In our case, it was 0.1 seconds. With those numbers, you can figure out, okay, I need 32 workers and read ahead of 3. And from there, you put those numbers in and like you get saturation of your training loop. So this is my last slide. How could you make this even faster? So this is still feels fairly rudimentary, although it works, so it's cool. There's a lot more you could do on the caching side. So each chunk was, what did I say, 10 megabytes, but we were only keeping a small fraction of that, about 4 or 5% of each of the chunks we read were used in that batch. So the more you can cache those chunks that you've already read, most of the time is spent like going to Google Cloud Storage and decoding the data. So the more you can cache those chunks, the faster things will be. You could imagine a shared memory cache instead of a single process cache or a per process cache, or you could spill to SSD and use that cache. So there's definitely something you could do there. Custom sampling. Our sampling here was completely random, meaning like we very rarely revisited the same part of the data set, which means caching didn't help very much. But if you were willing to revisit regions a little more frequently, you could utilize caching more. Of course, you could throw more CPUs at this, or you could even get lucky and have like more efficient chunking, or maybe you create more efficient chunking somehow. But in our case, like the chunk reads and the batch size, or the chunk sizes and the batch sizes were not well aligned. And so we did a lot of reading of data that we didn't end up using. And I'd love to hear your ideas on other things that folks have tried that have worked or not worked very well. Here's my email. Everyone knows how to find me. But yeah, I'll stop there and answer some questions and go from there.
All right, thanks, Joe. I'm going to stop